Hello, this is Rick from MathX, and today we're going to be doing the number 22 from the AMC 12A of 2021. Now, this is actually a pretty cool trig problem, because even though it looks terrifying, it actually has a pretty nice and elegant solution. And the motivation to get there isn't that tricky either. So without further ado, let's just get into it. Suppose the roots of the polynomial p of x equals x cubed plus ax squared plus bx plus c are cos of 2 pi by 7, cos of 4 pi by 7, cos of 6 pi by 7, where the angles are all in radians. What is ABC? So this problem is really simple. It's one of those problems on like the AMC. You see it and you know pretty much what's going on. We have a polynomial and we know what its roots are. And based on that information, we have to calculate a couple of the coefficients of given polynomial. The first thing that we should notice in this problem are that the cost values that they give us are pretty terrible actually. Typically in an AMC 12 trig problem, when they want you to do direct computations with the costs or signs, they're going to give you better values like pi by 6, pi by 3, values that we know how to compute for. But pi by 7, we shouldn't attack this from just a purely computational standpoint. We should think about what tricks we can manipulate to make these costs easier to deal with. So this motivates us to use complex numbers. So doing so, we set up the complex number z equals e to the I 2 pi by 7. So now that we have the complex number overall, we can find out the cost component of this complex number by just taking the real part of it. So we can write real part of z is equal to cos of 2 pi by 7. And for any n that multiplies in with the 2 pi by 7, z will be raised to that same power. Furthermore, since cosine itself is an even function, we can simply further expand this to say that the real part of z to the minus n is also equal to cos of 2 pi n by 7 because of just cosine being an even function. So this means that we can compute each of cosine of 2 pi to the n by 7 as simply z to the n plus z to the minus n by 2. Since when we add both of these parts together, the complex parts will cancel each other. Since when we add these two terms together, the imaginary parts will cancel each other out. The real cosine parts will get multiplied twice, and then when we divide it by 2, it's just going to give us our original cosine out again. So we can generate each of cosine of 2 pi by 7, 4 pi by 7, and 6 pi by 7 this exact same way. So in the case of 2 pi, n is equal to 1. So we'd write this as z to the positive 1 plus z to the minus 1 by 2 with 4 pi by 7. We'd write it as z squared, since remember, here we're going to have n equals to 2, plus z to the minus 2 by 2. And then for 6 pi by 7, since we're having n equals to 3 in this case, we're going to set it to z cubed plus z to the minus 3 by 2. Now, since the roots of unity really only goes from n equals 0 to n equals 6, and pretty much these minus terms are just other ways of just saying all of these terms from 0 to 6, we know that minus 1 is really just z to the 6th. Minus 2 is really just z to the 5th. And minus 3 is really just z to the 4th. So what this really tells us is that the summation of cos two pi to the n by 7, where n is just 1 to 3, this is just simply the summation of 1/2 times z n, where n goes, in this case, from 1 to 6. So pretty much it's just asking us to add up. So pretty much this just tells us that cos of 2 pi by 7 plus cos of 4 pi by 7 plus cos of 6 pi by 7 is simply equal to 1/2 of 1/2 times the first root of unit, the first seventh root of unity, plus 1/2 times the second seventh root of unity, all the way to the sixth seventh root of unity. Since we're excluding z to the 0 here, which is equal to 1, and we know that the sum of the roots of unity from z0 to z6 is equal to 0, and we exclude z0, we know that the summation of z1, z to the first, plus z squared, plus z cubed, all the way to z to the sixth, will simply be equal to minus 1. Because with z to the 0, which is 1, it would be equal to 0. So without z to the 0, it would just be minus 1. So pretty much the summation just tells us that cos of 2 pi by 7 plus cos of 4 pi by 7 plus cos of 6 pi by 7 is equal to minus 1. So I wrote it here in sigma notation and using the complex numbers. I can write it once again here, just for everyone to see. So just a quick recap, we got this equation by expressing the cosine as the real part of each of the seventh roots of unity using the even property of these roots of unity to just write an expression that incorporates z to the first, z to the second, where z is the uh first is one of the roots of unity, one of the seventh roots of unity, and from there we use the fact that the summation of z to the 0 plus z to the 1 all the way to z to the 6 is 0. Since z to the 0 isn't there, that means z to the 1 plus z to the 2 all the way to z to the 6 is minus 1. So then we just set that equal to our original cosine and just divide it by 2. So this is how we got to this point. And then once you get to this point, you're in a major benchmark in the problem. It's from here that you can separate into different paths on what to do and how to solve this problem. So there are multiple ways of going about this problem from this point. However, I would like to do the slickest way that I found on the internet. So basically from here, we can just recognize that this equation is of the form of cos of theta plus cos of 2 theta plus cos of 3 theta. And then we set that equal to negative 1/2. Well, the interesting thing is that if we just set cos theta to x, we're going to have cos of 2 pi by 7, cos of 4 pi by 7, and cos of 6 pi by 7 be the roots of the resulting polynomial. So doing that and expressing this entire thing in terms of x, where we just set cos of theta to x, we get cos of theta x plus cos of 2 theta. So the double angle formula for cos has multiple different forms. However, since we want to keep it in terms of cos theta, we're going to use the double angle formula form, in which cos of 2 theta equals to 2 cos squared theta minus 1. So writing it here, we'd get 2x squared minus 1. So this is just how we would substitute the cos 2 theta into this. And then finally for cos 3 theta, we're just going to use the triple angle formula, which if you have a tough time remembering on the test, remember there's a nice proof I encourage you to search up using complex numbers. So triple angle formula, definitely something that you should worth noting. You should worth noting for the test. Cos of 3 theta is equal to 4 cos theta cubed minus 3 cos theta. And yeah, if you just have trouble remembering this one, just look up the proof, and then after you understand the proof using complex numbers, there's no way you can forget this. So substituting x back in for cos theta, we get that this cos 3 theta turns into 4 cos cubed theta minus 3 cos theta. With cos theta as x, we got 4x cubed minus 3x. And then we set that equal to negative 1/2. Rearranging this polynomial into a better, more appropriate form, we get 4x cubed plus 2x squared minus 2x plus 1, minus 1 plus 1/2 minus 1/2 is equal to 0. But the problem with this is, in the original problem, they showed the coefficient of x cubed to be 1. So we have to divide through the entire thing by 4. So we get x cubed plus 1 half x squared minus 1 half x minus 1/8. Now here's the good thing. Remember, this is the equation that we generated with the idea that its roots were cos of 2 pi, cos of 4 pi, and cos of 6 pi. And we just did this by just generalizing it. So doing that, we got a cubic in between, but then simplifying it, we get our cubic, which appears to have the same form as the one provided in the problem. So instead of doing any like creative Vietnamese things, we can just take the coefficients as they are and just multiply them together. So we have coefficients of 1 half, negative 1 half, and negative 1/8. So 1 half times negative 1 half times negative 1/8 will just give us 1 over 32. Which is our answer choice D. So this problem was pretty cool actually. To do this, we had to use not only trig, but we had to use a thorough understanding of complex numbers. And even though it wasn't easy per se, it's what you'd expect from an AMC 12 number 22. And if you have a solid background in both trig and complex numbers, you should be able to pull this off with not too much difficulty. The solution itself wasn't too convoluted or bashy. It just requires you to know the trig identities inside out and know how to exploit complex numbers to make trig easier. You need to know how to find the cost component of a complex number. You like in the Euler's form, um you need to know how to sum up the different parts of a complex number, how to sum up the different roots of unity. And you just need to know a different number of different clever manipulations with both trig and complex numbers. So nothing too crazy, but overall it's quite an interesting problem, and it makes you think and realize what you should learn for the test and what is worth spending some time into. So thank you for watching, and I hope you enjoyed the video.